Hello, this is Clayton Balmus, and I'm here to share with you as your teacher in our audio classroom here today at SynMax University, available at synmaxperformancelubricants.com. Today, we're going to be talking about the Racing and Commercial Coolant System, Part 1. Now, we've got many parts to this coolant system overall teaching presentation. But today in Part 1, it's going to be broken down to two sections, A and B. So now we're going to talk about horsepower, BTU, and heat energy. Energy equals heat generated, which is BTUs. You see, the higher the horsepower, the more BTU and heat energy you have to transfer or disperse. Now in this presentation, we're going to be talking about the coolant system. But this theory also applies to all components, which would include your transmission, either manual or automatic, your differential, your axles, or any component. When you create energy, you create heat, and that heat has to be transferred and dispersed for success. Anyway, let's continue on. The act of the energy is this. When you have horsepower, it creates BTU heat, or we have heat energy. The summary is this. The more energy you create, or horsepower, the more BTUs which need to be dispersed. In general, if you wanted to create a BTU factor to know what the horsepower to BTU ratio would be, if you had, let's say, a 2-valve production engine, that number would be 42.42, and then you multiply it times 0.6. So here's the example. Let's say you had a 2-valve engine, and it was running at 200 horsepower. You'd multiply that times 42.42 times 0.6, and you'd get about 5,000 BTUs. So if you had a 800 horsepower engine, well, guess what? You'd have like 20,000 BTUs. So there you go. Now, heat transfer performance. When you run cooler, you'll last longer. Racing conditions using a premium chemistry treatment with 100% clean, purified water produces the following. You will increase the coolant system efficiency by 10 to 15%. The water temperature with the thermostat open should run about 190 degrees, and this is without what we would call a heat soak or high extreme duty situation. Now this also, other than racing, would work for these theories for the military or any high temperature application you're trying to deal with. Now, the previous water temperature with a non-treated tap water could be, let's say, 215 or 210 degrees. You see, the basic scientific theory is this. Above 160 degrees Fahrenheit, when you reduce the operational temperature 10 centigrade or 18 Fahrenheit, depending upon the specific decomposition rate, the overall component life will increase greatly. You see, it's called convection. Here's the definition. It is the transference of heat within a fluid by the actual movement of the heated molecules from one place to another. See, a considerable amount of available heat energy, or BTUs, must be relieved from the combustion chamber parts or the metal surfaces areas by the heat transfer or convection process. This heat transfer or convection process is performed by the coolant system dispersing the heat energy into the atmosphere through the radiator. I'm going to repeat that again. The heat transfer process is performed by the coolant system dispersing the heat energy into the atmosphere through the radiator. That's why we call it a heat exchanger. Energy equals heat generation. Keep the cylinder chamber cool and efficient for performance repeatability. This heat rejection or transfer process is necessary in order to prevent thermal metal fatigue of the pistons, cylinder walls, cylinder head, and other components. You see, when the metal gets hot, the pores open up. When it's cold, they're closed. So if we can be able, in the slightest percentage of way, maintain a consistency, it's a good thing. Furthermore, the center cylinders normally are going to be running hotter than the front or rear outside cylinder areas. So if we can be able to increase the chemistry and coolant system efficiency, it helps all the cylinders, no matter where they're at, have a much greater even playing field to perform. Again, higher horsepower equals higher heat transfer needs. In the combustion chamber area, here's the requirements. The cylinder area must be cooled and lowered enough to prevent pre-ignition and detonation or the dieseling effect. See, we run right at the edge of what we call, our 15 or 16 to 1 fuel to air ratio. We want all of the cylinders to work at optimum efficiency. You see, this takes place with a computerized modern fuel injection system because it has a knock sensor which automatically retards the ignition and fuel injection timing to prevent this pre-ignition. Remember the days long ago, or even in your classic hot rod or your older vehicle, you'd hear that rattling going on, with your carbureted vehicle? Well, you couldn't do a thing about it except, back your foot out, right? Anyway, like I said, this problem or solution is not available for the standard carburetor. You see, the fact is this: the higher the combustion chamber temperature, the higher the octane number, which is required to prevent the pre-ignition or detonation. You see, the higher the octane number, the slower the burn. Since the immediate availability of a higher octane fuel is limited, for the requirement, increased temperatures within the combustion chamber requires retarding of the spark timing, which reduces peak torque and power available. You see, here's the problem. When you have a higher combustion and an inlet temperature, with reduced humidity and density, or in other words, the amount of water and oxygen suspended in the air, it reduces the ability to cool the combustion chamber and performance quality of the fuel-air mixture. Now, on a side note, a lot of people talk about oxygenating the fuel, which is true to overcome this situation. But oxygenation of the fuel really doesn't come into play until you're about 80 degrees Fahrenheit. Anything below it doesn't matter. Furthermore, people like to try to put in oxygenation additives into the fuel. Well, there's two theories I want to have on that. First, the Environmental Protection Agency in a street vehicle will require, as of 1979, the fuel to be at only 1/4% of oxygenation, and that even applies today here into the 2011 plus time period. So they're not going to change that rule. Another thing is this: if you have a computerized vehicle, it's going to sniff out and sense the oxygen and recalibrate the fuel to air ratios anyway. So there's no advantage there. The last of all is that in your carbureted racing situations that you would have, all right, in your carburetor, unless you have a really good person that's a carburetor specialist right there that can be able to sense the air and the humidity along with the oxygenation you're put in, you're going to be lowering your BTU ratio. It's a real problem. So stick with the fuel that works and the additive package that's best. And once it's set, don't be monkeying with it, because if you get too lean, it could be a problem. All right. So what we're here to do with the coolant system is that a cooler combustion temperature environment will increase performance efficiency for more horsepower and torque. In other words, when the coolant system's working better, we have a much greater level playing field for all the cylinders to work with performance repeatability. You see, we need to increase the heat BTU energy transfer flow. When we do this, we will increase the engine performance and component durability. Here's the fact. Maximum engine performance requires the coolant and radiator system, in other words, heat transfer, to continually and efficiently absorb, reject, and disperse the created heat energy 2 to 3 times the amount that was produced. Problem is when you reduce the flow of heat through the coolant system, in other words, it's not working properly to dissipate the energy and heat. It reduces efficiency, performance, and component durability. We have to increase the heat transfer capability. Now, Clayton, is that a bigger radiator? No. When you have maximized the efficiency and gone through all your cross tubes and all those kinds of things, which is helpful, you need to have the most advanced water chemistry science available. And those selections of that advanced chemistry is available through the water cooler program. Thermal properties. Each material component has its own material density and thermal property performance. For instance, aluminum is at 2.7, where cast iron is at 7.25. So aluminum can disperse energy, heat energy, 3 times better than steel. Think about it. Now, most heat is transferred in a cooling system by convection from a hot metal surface to a cooler liquid. In other words, the coolant system water passages in the engine block through the components. And from a hot liquid, in other words, the coolant system, to a cooler metal surface or the radiator. Very simple. We shared it before. With the right chemistry, it's able to grab the heat from the cylinder head and the cylinder walls and those important areas, take it to the radiator, to the cooling tubes, right there, and then it touches the surface of those cooling tubes to remove the heat. Now, most of the engines out there are going to have steel blocks. Now, why do you think they have an aluminum radiator? Because it disperses the heat. Think about that one. Now, here's another thing. The neutral purified water alone has amazing superior heat transfer properties as compared to any other liquid cooling medium. So if somebody tries to share something with you that's an oil, maybe that'll work in a commercial application, but not in the engine department. Purified water alone has double the heat transfer capability as compared to glycol. We're going to share about this in other presentations. Now, to help along with the purified water in its conductivity of its thermal abilities, we have to be able to use advanced science chemistry, and that's available through the water cooler. Here's a product here that's a concentrate. It's good for 2 or 3 gallons. You use it with the purified water. It will double the performance of water, okay, the purified water. And it is able to do everything shared in here, especially improving coolant system efficiency, heat transfer capability, and etc. If you want something easier with a simple pour and go, we've got the 100% premix, the exact chemical concentration with the purified water, 100% direct in racing. If you've got an all-weather application, you can use 1 gallon of premix to 1 gallon of glycol. This is for standard diesel, biofuels, doesn't matter. And it's a tremendous product for the turbocharger and supercharger intercooler performance application. So this presentation is going to be continued to section B, which is for heat transfer performance. I wanted to thank you for the time that we have together. So this is Clayton Balmas here with SynMax University at synmaxperformancelubricants.com, and I encourage you to look at our other presentations to give a little more information and education to make proper decisions to increase our coolant system performance. For technical test, and brochure information on how the Aerospace Advantage for Motorsports can work with your race team or other commercial requirements, please visit us at synmaxperformancelubricants.com.